So our problem with this answer is sort of a fundamental problem that 2 seconds is way too long. We want to know how fast was the fly going at the moment when t equals 2. And we're having to include all these garbage wrong answers after t equals 2, when what we really want to know is what's happening at this moment. So I still don't know how to cut it down to a moment, but I can at least throw away some of the garbage and ask what's going on. How about from t equals 2 to t equals 3? Our first estimate was how fast was the fly going over these 2 seconds when we really only wanted 1 moment. I can cut that down to 1 second. It's still infinity times too big. I want to know what's happening at a moment. A second is infinitely longer than a moment, 1 divided by 0 or something. But it's going to be better than the last answer. If I knew our answer was something smaller than 6, and I keep getting it's smaller than this and then smaller than this, that's more and more information about the answer to the question we want. So let's try this out. The thing we're working out is how far did the fly go? S of 3 is 9, S of 2 is 4. The gap between those is 5 inches, that's a 5, in that 1 second. So now our estimate is 5 inches per second. 5 over 1. And that's a better estimate. But a second is still infinity times too long. I can ask how about from t equals 2 to t equals 2.5. I can ask about half a second. I take S of 2. I take S of 2.5. What's 2.5 squared? 2.5 squared is... $6.25. I want to subtract those. 6.25 minus 4. And then divide by how long did it take to get from 2 to 2.5? That's 1/2 of a second. So I'm dividing that by 0.5. I want to take that number, subtract 4, and then divide that by 0.5 seconds is how long it took to do that. And I get 4.5. Where exactly did this number come from? Let's take a second to notice our formula that we're plugging this into. That 4.5 came from a fraction. The fraction is going to be called a difference quotient. It's called a difference quotient because it's a quotient of differences. That 0.5 on bottom was from being 2.5 minus 2. The numbers on top, 6.5 minus 4, those came from being s of 2.5 minus s of 2. It was a difference of y values over difference of x values. The reason you talked about slope in an algebra class was because it gave you the rate of change of something. And that gave us 4.5. Again, half a second is infinity times too long. We've worked out that our answer should be something less than 6, and then for the same reason it should be something less than 5, and then it should be something less than 4.5. And we keep shrinking this down. The only interesting trick we have in calculus is we can't get the answer that we want, but we can get something close. And the fundamental trick of calculus is saying, I don't need to be able to compute the actual answer I want. It is enough to be able to get closer and closer and closer. To be able to do more and more calculations that give you more and more accurate estimates is a way of defining the number itself. How about from t equals 2 to t equals 2.1? What's s of 2.1 minus s of 2 divided by 2.1 minus 2? The number on bottom is 0.1. The number on top is 2.1 squared minus 2.1 minus 2 squared. I ask my calculator, hey calculator, what is 2.1 squared minus 2 squared I know is 4. Divide that by 0.1. We're getting 4.1. That's how fast the fly was going over the course of 1/10 of a second. My calculator's really good at this. How about if I go from t equals 2 to t equals 2.0001? Let's jump down to, what is this, a 10,000th of a second? How fast is the fly going over this period? I'm asking my calculator, what is 2.0001 squared minus 2 squared is 4. Divide that by 0.0001. I get 4.0001. So let's try and sum up these. From t equals 2 to, when we went from 2 to 4, we had an average speed of 6. When we went from 2 to 3, it was down to 5. When we went 2 to 2.5, it went down to 4.5, I think it was. When we went to 2.1, we got 4.1. When we went to 2.0001, it sort of jumped to the end and went crazy. That's not the end, by the way. Oh, my thing crashed. Oh, yeah, is you still there? How much? So, if we make a chart of all the computations we've done, we were taking how fast was the fly moving over, like what was his average speed over an interval of length 2 seconds, then 1 second, then half a second, then 1/10 of a second, then 1/10,000th of a second. And the answers we got, which we think are getting closer and closer to the correct answer, are his average speed was 6 inches per second, and then 5 inches per second, and then 4.5, and then 4.1, and then 4.001 inches per second. We can get excited about noticing the pattern here, like that 0.001 becoming that 0.001 is probably not a coincidence, but I don't want to focus too hard on that, because that pattern is easy to spot for the function x squared we noticed, and very often it's going to be much harder to spot, so we don't want to get too focused on that aspect of it. The thing I do want to focus on is that these numbers look like they're getting closer. We'll say the word approaching for getting closer and closer. 4 as an answer. So maybe this seems like it's some evidence that if I was able to shrink it down to a moment, which is not a computation we can actually do, but if we could, the answer we would get seems like it's 4. So our guess is the fly's speed at the moment t equals 2 is 4 inches per second. 4 happens to be a number we can recognize. If we'd found it was getting closer and closer to 1.93314, I wouldn't be able to recognize that number as exactly whatever it is. Sometimes the number is a number that I can recognize if you show me a bunch of digits. 4 is easy to recognize if you give me the first 30 digits. I can make the guess, probably the answer's 4. Sometimes you're lucky in that way, sometimes you're not. We'll see more and more tricks around that. But that's the fundamental idea. And this is what the derivative is. In this context, we're going to say s prime of 2 equals 4. Let's state the definition of a derivative. The derivative, or let's say, what do we need to take the derivative of? We need a function defined at a point. Suppose f of x is a function defined at some specific point and defined near that point, some point that we will call x naught, x sub 0, the